Open a map on your phone, and within seconds, a blue dot appears. It may know which side of the road you are standing on. It can follow a car through a city, guide an aircraft across an ocean, or help a rescue team find someone in the wilderness. But no satellite is taking a picture of you. Your phone is not sending its location into space and waiting for an answer. GPS works in almost the opposite way. The satellites broadcast, your phone listens. Then it solves a timing problem so precise that an error of 1/1,000,000th of a second could move your location by hundreds of meters. The Global Positioning System is a constellation of satellites orbiting about 20,000 kilometers above Earth. Each satellite carries atomic clocks and continuously transmits a radio signal. That signal contains two crucial pieces of information: where the satellite is and exactly when the signal was sent. Radio waves travel at the speed of light. So if your receiver knows the sending time and measures the arrival time, it can estimate how long the signal traveled. Travel time multiplied by the speed of light gives distance. The distance is not perfectly exact, so engineers call it a pseudo-orange, but it is the raw measurement from which your position is built. Knowing your distance from one satellite does not reveal one location. It means you could be anywhere on the surface of an enormous imaginary sphere centered on that satellite. A second satellite creates another sphere. Their intersection narrows the possibilities to a circle. A third satellite narrows the solution further. In a perfect world, 3 distance measurements could determine a 3-dimensional point. But your phone does not contain an atomic clock. Its tiny clock is cheap, practical, and slightly wrong. Because the signal moves so fast, even a tiny clock error becomes a large distance error. That is why a GPS receiver normally needs at least 4 satellites. The fourth measurement allows it to solve 4 unknowns at once: latitude, longitude, altitude, and the error in its own clock. The calculation only works if the receiver knows where every satellite really is. That information is maintained by a global control network on Earth. Monitoring stations track the satellites. Control systems calculate their precise orbits, check their clocks, and upload updated navigation data. The satellite then broadcasts that information to users below. So the blue dot is not created by a phone alone. It depends on 3 connected layers: satellites in space, control stations on Earth, and a receiver in your hand. Remove any one of those layers, and the system stops working. The clocks face another problem. Time does not pass at exactly the same rate in orbit as it does on Earth. Because the satellites move rapidly, special relativity makes their clocks run slightly slower. Because gravity is weaker at their altitude, general relativity makes the clocks run faster. Combined, GPS satellite clocks would run about 38 microseconds per day faster than clocks on Earth. That tiny difference is enough to make positioning errors grow rapidly, and useful navigation would collapse. Every time your phone finds the blue dot, it is quietly relying on Einstein's description of time. Even with perfect mathematics, the signal must survive the real world. The atmosphere can delay it, buildings can block it or reflect it. Trees, bridges, mountains, and poor satellite geometry can reduce accuracy. Deep indoors or underground, the receiver may not see enough satellites at all. Under open sky, a typical smartphone may locate itself within several meters. In a city street surrounded by tall buildings, the same phone can appear on the wrong road. Modern phones reduce these problems by combining signals from GPS with other satellite navigation systems. They may also use cell towers, Wi-Fi networks, motion sensors, and downloaded assistance data to find a faster or more stable solution. So the blue dot on a phone is often a fusion of technologies. GPS remains the global reference, but it is not always working alone. GPS does not literally work everywhere. It works globally when a receiver has a usable view of the sky and can hear enough satellites. It does not need a mobile data connection to calculate coordinates, although maps, traffic, and search results may need the internet. And the satellites do not know who is listening. A basic receiver is passive. It only receives the broadcast and performs the calculation locally. That simple design is one reason the system can serve enormous numbers of users at the same time. GPS began as a military navigation project, but the hidden system now supports far more than directions. Precise GPS time helps synchronize communication networks, power systems, scientific instruments, and other infrastructure. Location is only one product of a much deeper timing system. The blue dot feels immediate and personal, but it is produced by atomic clocks, orbital mechanics, radio engineering, global ground control, relativity, and a receiver solving equations in fractions of a second. GPS does not look down and find you. It tells your device what time it is from several places in space. Your device turns those differences in time into distances, and those distances into one point on Earth. The blue dot is geometry built from time.